put in a marker. All right, and let's go ahead and turn off the stack game for right now. And then let's go ahead and get going here. So today's chapter is Dirty Flag. Intent. Avoid unnecessary work by deferring it until the result is needed. Motivation. Many games have something called a scene graph. This is a big data structure that contains all of the objects in the world. The rendering engine uses this to determine where to draw stuff on the screen. At its simplest, a scene graph is just a flat list of objects. Each object has a model or some other graphic primitive and a transform. The transform describes the object's position, rotation, and scale in the world. To move or turn an object, we simply change its transform. The mechanics of how this transform is stored and manipulated are unfortunately out of scope here. The comically abbreviated summary is that it's a 4x4 matrix. You can make single transform that combines two transforms, for example, translating and then rotating object by multiplying the two matrices. How and why that works is left as an exercise for the reader. That's not quaternion math, right? Or is that? I can't remember. Like, I know that quaternion math comes in a lot for like three-dimensional graphic stuff. And I haven't really done any three-dimensional graphic stuff, so I've never run into that. I just heard other game developers complaining about it every once in a while. When the renderer draws an object, it takes the object's model and applies the transform to it, and then renders it there in the world. If we had a scene bag and not a scene graph, that would be it, and life would be simple. However, most scene graphs are hierarchical. An object in the graph may have a parent object that it is anchored to. In that case, its transform is relative to the parent's position and isn't an absolute position in the world. For example, imagine our game world has a pirate ship at sea. Atop the ship's mast is a crow's nest. Hunched in that crow's nest is a pirate. Clutching the pirate's shoulder is a parrot. The ship's local transform positions the ship in the sea. The crow's nest transform positions the nest on the ship, and so on. Okay, so we have our ship, we have our captain, and we have our parrot. So pirate ship, crow's nest. Oh, I guess like this thing also. Then a parrot, then a parrot. I mean, he says programmer art, but I mean, this is better than the art that I've tried to draw. This way, when a parent object moves, its children move with it automatically. If we change the local transform of the ship, the crow's nest, pirate, and parrot go along for the ride. It would be a total headache if, when the ship moved, we had to manually adjust the transforms of all the objects on it to keep them from sliding off. To be honest, when you are at sea, you do have to keep manually adjusting your position to keep from sliding off. Maybe I should have chosen a drier example. But to actually draw the parrot on screen, we need to know its absolute position in the world. I'll call the parent relative transform the object's local transform. To render an object, we need to know its world transform. Local and world transforms. Calculating an object's world transform is pretty straightforward. You just walk its parent chain, starting at the root all the way down to the object, combining transforms as you go. In other words, the parent's world transform is, okay, so the parent world is the ship local. Is this really times? Ship local times? Or is it just just going up? So the world parrot is ship local, nest local, pirate local, parrot local. In the degenerate case where the object has no parent, its local and world transforms are equivalent. We need the world transform for every object in the world every frame. So even though there are only a handful of matrix multiplications per model, it's on the hot code path where performance is critical. Keeping them up to date is tricky because when a parent object moves, that affects the world transform of itself and all of its children, recursively. The simplest approach is to calculate transforms on the fly while rendering. Each frame, we recursively traverse the scene graph starting at the top of the hierarchy. For each object, we calculate its world transform right then and draw it. But this is terribly wasteful of our precious CPU juice. Many objects in the world are not moving every frame. Think of all the static geometry that makes up the level. Recalculating their world transforms each frame, even though they haven't changed, is a waste. Cached world transforms. The obvious answer is to cache it. In each object, we store its local transform and its derived world transform. When we render, we only use the pre-calculated world transform. If the object never moves, the cache transform is always up to date, and everything's happy. When an object does move, the simple approach is to refresh its world transform right then. But don't forget the hierarchy. When a parent moves, we have to recalculate its world transform and all of its children's recursively. Imagine some busy gameplay. In a single frame, the ship gets tossed on the ocean, the crow's nest rocks in the wind, and the pirate leans to the edge, and the parrot hops onto his head. We change 4 local transforms. If we recalculate world transforms eagerly whenever a local transform changes, what ends up happening? So yeah, we move the ship, and then we have to recalculate the ship's location, recalculate the nest, recalculate the pirate, recalculate the parrot. But of course, we removed the nest. So recalc the nest, recalc the pirate, recalc the parrot. Right, so basically the ship moved, so then we moved the nest, and then because the ship moved, we also lean the nest. And then of course the parrot gets recalculated how many times? You can see on the lines marked star that we're recalculating a parrot's world transform 4 times when we only need the result of the final one, this one down here. We only moved 4 objects, but we did 10 world transform calculations. That's 6 pointless calculations that get thrown out before they're ever used by the renderer. We calculated the parrot's world transform 4 times, but is only rendered once. The problem is that a world transform may depend on several local transforms. Since we recalculate immediately each time one of the transform changes, we end up recalculating the same transform multiple times when more than one of the local transforms that depends on changes in the same frame. Deferred recalculation. We'll solve this by decoupling changing local transforms from updating the world transforms. Okay, so decoupling local transforms, and so they won't trigger world transforms right away, at least. This lets us change a bunch of local transforms in a single batch, and then recalculate the affected world transform just once after all of those modifications are done, right before we need it to render. It's interesting how much of software architecture is intentionally engineering a little slippage. To do this, we add a flag to each object in a graph. Flag and bit are synonymous in programming. They both mean a single micron of data that can be in one of 2 states. We'll call those true and false, or sometimes set and cleared. I'll use all of these interchangeably. When the local transform changes, we set it. When we need the object's world transform, we check the flag. If it's set, we calculate the world transform and then clear the flag. The flag represents, is the world transform out of date? For reasons that aren't entirely clear, the traditional name for this out of dateness is dirty, hence a dirty flag. Dirty bit is an equally common name for this pattern, but I figured I'd stick with a name that didn't seem as prurient. I don't think let's see, is there a good search Google for that? Prurient, having or encouraging an excessive interest, okay. Interesting. Wikipedia's editors don't have my level of self-control and went with dirty bit. If we apply this pattern and move all of the objects in our previous example, the game ends up doing, okay, so we're gonna move the ship, move the nest, move the pirate, move the parrot. So basically we'd have like the nest saying like, hey, you're just going like this all the time. And pirate, you're like turning left, turning right, turning left. And the parrot, you're like randomly jumping up on the head of the captain, you're going into the shoulder and then other shoulder. And then when it comes to render, then we recalc all of this stuff once. But then each time we recalc, we check, hey, did we move? That's the best you could hope to do. The world transform for each affected object is calculated exactly once, with only a single bit of data. This pattern does a few things for us. It collapses modifications to a multiple local transforms along an object's parent chain into a single recalculation on the object. It avoids recalculation on objects that didn't move. And a minor bonus, if an object gets removed before it's rendered, it doesn't calculate its world transform at all. The pattern. A set of primary data changes over time. A set of derived data is determined from this using some expensive process. A dirty flag tracks when the derived data is out of sync with the primary data. It is set when the primary data changes. If the flag is set when the derived data is needed, then it is reprocessed and the flag is cleared. Otherwise, the previous cached derived data is used. When to use it. Compared to some other patterns in this book, this one solves a pretty specific problem. Also, like most optimizations, you should only reach for it when you have a performance problem big enough to justify the added code complexity. Dirty flags are applied to two kinds of work, calculation and synchronization. In both cases, the process of going from the primary data to the derived data is time-consuming, or otherwise costly. In our scene graph example, the process is slow because of the amount of math performed. When using this pattern for synchronization, on the other hand, it's more often that the derived data is somewhere else, either on disk or over the network or on another machine. And simply getting it from point A to point B is what's expensive. There are a couple other requirements too. The primary data has to change more often than the derived data is used. This pattern works by avoiding processing derived data when a subsequent primary data change would invalidate it before it gets used. If you find yourself always needing that derived data after every single modification to the primary data, this pattern can't help. It should be hard to update incrementally. Oh, okay, so wait. Basically, if like another local change or whatever relies upon this, like if we need it before the render, then we need to do it right away. We can't like delay it. It should be hard to update incrementally. Let's say the pirate ship in our game can only carry so much booty. We need to know the total weight of everything in the hold. We could use this pattern and have a dirty flag for the total weight. Every time we add or remove some loot, we set the flag. When we need the total, we add up all of the booty and clear the flag. But a simpler solution is to keep running total. When we add or remove an item, just add or remove its weight from the current total. If we can pay as we go, like this, and keep the derived data updated, then that's often a better choice than using this pattern and calculating the derived data from scratch when needed. This makes it sound like dirty flags are rarely appropriate, but you'll find a place here or there where they help. Searching your average game codebase for the word dirty will often turn up uses of this pattern. From my research, it also turns up a lot of comments apologizing for dirty hacks. Oh, that's too true. Bare Knuckle Waffle, good morning. Keep in mind, even after you've convinced yourself this pattern is a good fit, there are a few wrinkles that can cause you some discomfort. There is a cost to deferring for too long. This pattern defers some slow work until the result is actually needed. but when it is, it's often needed right now. But the reason we're using this pattern to begin with is because calculating that result is slow. This isn't a problem in our example because we can still calculate world coordinates fast enough to fit within a frame. But you can imagine other cases where the work you're doing is a big chunk that takes noticeable time to chew through. If the game doesn't start chewing until right when the player expects to see the result, that can cause an unpleasant visible pause. Another problem with deferring is that if something goes wrong, you may fail to do the work at all. This is particularly problematic when you're using this pattern to save some state to a more persistent form. For example, text editors know if your document has unsaved changes. That little bullet or star in your file's title bar is literally the dirty flag visualized. The primary data is the open document in memory, and the derived data is the file on disk. Many programs don't save to disk until either the document is closed or the application is exited. That's fine most of the time. But if you accidentally kick the power cable out, there goes your masterpiece. Editors that auto-save a backup in the background are compensating specifically for this shortcoming. The auto-save frequency is a point on the continuum between not losing too much work when a crash occurs and not thrashing the file system too much by saving all the time. This mirrors the different garbage collection strategies and systems that automatically manage memory. Reference counting frees memory the second it's no longer needed, but it burns CPU time updating ref counts eagerly every time references are changed. Simple garbage collectors defer reclaiming memory until it's really needed, but the cost is the dreaded GC pause that can freeze your entire game until the collector is done scouring the heap. In between the two are more complex systems like deferred ref counting and incremental GC that reclaim memory less eagerly than pure ref counting, but more eagerly than stop the world collectors. I think this is a positive of like some languages. Rust, for example, doesn't have a garbage collector, but at the same time, it does it at the end of every scope automatically. So it's basically just doing it as needed. So it's not like a huge amount of garbage being collected. Now, JavaScript, on the other hand, depending upon what engine we're talking about, in modern Chrome, I think starting with 10, I want to say, they moved the garbage collector into another thread on the system. I don't even know, maybe even another core, which means that you don't get that pausing anymore when you have a lot of objects to collect from memory. But it can still spike your if you have like a slow computer, it can noticeably increase like the speed of the fans and the battery drainage. You have to make sure to set the flag every time the state changes. Since the derived data is calculated from the primary data, it's essentially a cache. Whenever you have cached data, the trickiest aspect of it is cache invalidation, correctly noting when the cache is out of sync with its source data. In this pattern, that means setting the dirty flag when any primary data changes. Phil Carlton famously said there are only two hard things in computer science: cache invalidation and naming things. Miss it in one place, and your program will incorrectly use stale derived data. This leads to confused players and bugs that are very hard to track down. When you use this pattern, you'll have to take care that any code that modifies the primary state also sets the dirty flag. One way to mitigate this is by encapsulating modifications to the primary data behind some interface. If anything that can change the state goes through a single, narrow API, you can set the dirty flag there and rest assured that it won't be missed. You have to keep the previous derived data in memory. When the derived data is needed and the dirty flag isn't set, it uses the previously calculated data. This is obvious, but that does imply that you have to keep that derived data around in memory in case you end up needing it later. This isn't much of an issue when you're using this pattern to synchronize the primary state to some other place. In that case, the drive data isn't usually in memory at all. If you weren't using this pattern, you could calculate the drive data on the fly whenever you needed it, then discard it when you were done. That avoids the expense of keeping it cached in memory at the cost of having to do that calculation every time you need the result. Like many optimizations, then, this pattern trades memory for speed. In return for keeping the previously calculated data in memory, you avoid having to recalculate it when it hasn't changed. This trade-off makes sense when the calculation is slow and memory is cheap. When you got more time than memory on your hands, it's better to calculate it as needed. Conversely, compression algorithms make the opposite trade-off. They optimize space at the expense of the processing time needed to decompress. All right, it's time for our sample code. What I'm sure we've all been waiting for. Okay, sample code. Let's assume we met the surprisingly long list of requirements and see how the pattern looks in code. As I mentioned before, the actual math behind transform matrices is beyond the humble aims of this book. So I'll just encapsulate that in the class whose implementation you can presume exists somewhere out in the ether. All right, so let's go ahead and create a, this is gonna be dirty flag.js. Finally getting to those potentially louder or different keyboard sounds, because it has more of that classic clickety clackety of the, I think the red. I think the bottom of the keyboard actually tells me what it is. I don't know. Maybe I'm covering it up, or maybe it's somewhere else. Maybe it's on the other side. But okay, so we have class transform. And let's see. We're gonna have an origin method here. And we're gonna have a combine. That takes an other, and then it does something with it. The only operation we need here is combine. So we can get an object's world transform by combining all of the local transforms along its parent chain. It also has a method to get an origin transform, basically an identity matrix that means no translation, rotation, or scaling at all. Next, we'll sketch out the class for an object in the scene graph. This is the bare minimum we need before applying this pattern. Okay, so then we're going to have our graph node. So we're going to have our constructor here that takes a mesh. And we're going to store that internally. So this dot mesh equals mesh. We're also going to store a local by calling transform origin. Okay, so this dot local equals transform dot origin, like that. Now, right now, it's just going to be undefined because we don't know what this specifically returns and like what it does yet. Then obviously we have local and mesh that are private. We have children. Children is an array. And it looks like it's going to be whatever the max children are. So it's just purely an array at this point in time. And then we have the number of children. Okay, so I could see. Let's see. I wonder if we're doing this because it's like faster to not like mutate this array and like constantly change things off, but like reuse it over and over again. So what we can do here is have a const max children and set this equal to some number. Let's say like we have 5 children. We're not allowed to have more than 5 things sort of attached to each other. And then in this children here, we're going to do new array. And then the array length is max children. And then we're also going to have this dot num children, and we're going to set that to 0 to begin with because we have no children yet. Each node has a local transform which describes where it is relative to its parent. It has a mesh, which is the actual graphic for the object. We'll allow mesh to be null too, to have non-visual nodes that are used just to group their children. Finally, each node has a possible empty collection of child nodes. Okay, so hold on. If we have mesh can be null here, then we should have this be a default equals null. With this, a scene graph is really only a single root graph node whose children and grandchildren, etc. are all of the objects in the world. Okay, so we're gonna have essentially like in our function, like if we have this function set up, let's say, we might do this like let graph node graph. Okay, so if we have like sort of our graph, then inside of setup, I'm doing sort of like in P5.js style, we would do graph equals new graph node, and then it's going to be null for the mesh because the entire world isn't drawn out, just things inside of it would be. In order to render a scene graph, all we need to do is traverse that tree of nodes starting at the root and call the following function for each of the nodes mesh with the right world transform. Okay, so then we have render mesh, mesh and transform. Where is render mesh going to be? Is that in the graph node? Because it takes a mesh, and it takes a transform. Or is this just going to be down here like this? So function render mesh takes in a mesh, a transform, like that. We won't implement this here, but if we did, it would do whatever magic the renderer needs to draw that mesh at the given location in the world. If we can call that correctly and efficiently on every node in the scene graph, we're happy. An unoptimized traversal. To get our hands dirty, let's throw together a basic traversal for rendering the scene graph that calculates the world positions on the fly. It won't be optimal, but it will be simple. We'll add a new method to graph node. Okay, so we have a graph node here, and so here's a render. So, render, and now this takes a parent world. So we're gonna create a world. So const world equals this dot local, and then dot combine, and then the parent world. So the parent world here. So it's basically our combine, and then our local is this origin up here. which we don't exactly know what that is. Or at least I may have missed it. Like, because he didn't implement this. Let's see. Then we check if we have a mesh. So if this dot mesh, so if the mesh is not null, then we're going to call render mesh. We're going to hand this dot mesh and the world, which is the transform. Then we're going to loop through all the children and then call render on the children. So recursively render all the children. So for that in I guess, yeah, we do need the index. So index equals 0, index is less than this dot number of children, index plus equals to 1. Then we're just going to call this dot children of position index dot render and pass it in the world. We pass the world transform of the node's parent into this using parent world. With that, all that's left to get the correct world transform of this node is to combine that with its own local transform. We don't have to walk up the parent chain to calculate the world transforms because we calculate as we go while walking down the chain. We calculate the node's world transform and store it in the world. Then we render the mesh, if we have one. Finally, we recurse into the child's nodes, passing in this node's world transform. All in all, it's a tight, simple, recursive method. To draw an entire scene graph, we kick off the process at the root node. So then we have setup, and we'll probably have like an update. Or this is render, so this is going to be like a draw method, where we're going to say graph dot render transform dot origin. Let's get dirty. So this code does the right thing. It renders all the meshes in the right place, but it doesn't do it efficiently. It's calling local.combine parent world on every node in the graph every frame. Let's see how this pattern fixes that. First, we need to add 2 fields to graph node. So we have, let's see, graph node. So in graph node here, we take in the mesh, we store the mesh, store the local, and now we need a dirty. And we set dirty to true by default. We still have, in private, we're gonna have world be global here. So this dot world. Maybe we set this to like null to begin with. So that way, this dot world equals, okay, so then we do that. And then wherever we use world here, don't give me that. Okay, hold on. There we go. This dot world like that. The world field caches the previously calculated world transform, and dirty, of course, is the dirty flag. Note that the flag starts out true. When we create a new node, we haven't calculated its world transform yet. At birth, it's already out of sync with the local transform. The only reason we need this pattern is because objects can move. So let's add support for that. So in graph node, we have a set transform. So along with render here, now we're going to have a set transform. We're going to take in a local. So this dot local equals local. This dot dirty equals true. The important part here is that it sets the dirty flag too. Are we forgetting anything? Right, the child nodes. When a parent node moves, all of its children world coordinates are invalidated too. But here we aren't setting their dirty flags. We could do that, but that's recursive and slow. Instead, we'll do something clever when we go to render. Let's see. So here in render, we take in the parent world, and we're also going to take in the dirty. I don't know what that means. Hold on. Let's see. That's not C++. Oh, cool. It still found it. Bitwise inclusive or and assignment operator. So C pipe equals 2 is the same as C equals C or 2. Is that right? Am I reading that correctly? So it's or equals. Oh, inclusive or and assignment operator. C equals C or 2. Let's just pipe on its own. Binary OR operator copies a bit if it exists in either operand. Okay, so it's sort of like double pipe in JavaScript. So we don't exactly have that for real, but okay. So if dirty is not set it to be whatever dirty is. And interesting. So we're going to take in dirty like this. So if this is undefined here, okay, so if it's set, keep it what it is. I think what I can do here is do this dot dirty like that, and that replaces that. Where I can say, okay, if dirty exists and is passed in, we keep that. If dirty is not passed in, we take whatever is already stored internally. Then we check immediately if this dot dirty, or I guess if dirty, then we're going to do world combine, and then also this dot dirty equals false. So combine everything together. Then after that, we render the mesh, and we loop through everything, and we call render, and we also pass in dirty. There's a subtle assumption here that the if check is faster than a matrix multiply. Intuitively, you would think it is. Surely testing a single bit is faster than a bunch of floating point arithmetic. However, modern CPUs are fantastically complex. They rely heavily on pipelining, queuing up a series of sequential instructions. A branch like our if here can cause a branch misprediction and force the CPU to lose cycles, refilling the pipeline. The data locality chapter is more about how modern CPUs try to go faster and how you can avoid tripping them up like this. Chantilly, good morning, good morning. This is similar to the original naive implementation. The key changes are that we check to see if the node is dirty before calculating the world transform, and we store the result in a field instead of a local variable. When the node is clean, we skip combine completely and use the old but still correct world value. The clever bit is that dirty parameter. That will be true if any node above this node in the parent chain was dirty. In much the same way that parent world updates the world transform incrementally as we traverse down the hierarchy, dirty tracks the dirtiness of the parent chain. This lets us avoid having to recursively mark each child dirty flag in set transform. Instead, we pass the parent's dirty flag down to its children when we render, and look at that too to see if we need to recalculate the world transform. The end result here is exactly what we want. Changing a node's local transform is just a couple of assignments, and rendering the world calculates the exact minimum number of world transforms that have changed since the last frame. Note that this clever trick only works because render is the only thing in GraphNode that needs an up-to-date world transform. If other things accessed it, we'd have to do something different. Design decisions. This pattern is fairly specific. There are only a couple of knobs to twiddle. When is the dirty flag cleaned? When the result is needed. It avoids doing calculation entirely if the result is never used. For primary data that changes more frequently than the derived data is accessed, this can be a big win. If the calculation is time-consuming, it can cause a noticeable pause. Postponing the work until the player is expecting to see the result can affect their gameplay experience. It's often fast enough that this isn't a problem, but if it is, you'll have to do the work earlier. At well-defined checkpoints. Sometimes there's a point in time or in the progression of the game where it's natural to do the deferred processing. For example, we may want to save the game only when the pirate sails into port, or the sync point may not be part of the game's mechanics. We may just want to hide the work behind a loading screen or a cut scene. Doing the work doesn't impact the user experience. Unlike the previous option, you can often give something to distract the player while the game is busy processing. You lose control over when the work happens. This is sort of the opposite of the earlier point. You have micro-scale control over when you process, and you can make sure the game handles it gracefully. What you can't do is ensure the player actually makes it to the checkpoint or meets whatever criteria you've defined. If they get lost or the game gets in a weird state, you can end up deferring longer than you expect. In the background. Usually you start a fixed timer on the first modification and then process all the changes that happen between then and when the timer fires. The term in human-computer interaction for an intentional delay between when a program receives user input and when it responds is hysteresis. Hysteresis? You can tune how often the work is performed. By adjusting the timer interval, you can ensure it happens as frequently or infrequently as you want. You can do more redundant work. If the primary state only changes a tiny amount during the timer's run, you can end up processing a large chunk of mostly unchanged data. You need support for doing work asynchronously. Processing the data in the background implies that the player can keep doing whatever it is that they're doing at the same time. That means you'll likely need threading or some other kind of concurrency support, so the game can work on the data while it's still being played. Since the player is likely interacting with the same primary state that you're processing, you'll need to think about making that safe for concurrent modification too. I can see this as like when we're saving like state to disk. If that's very similar to like taking a backup of a database. If people are like constantly making changes to that database, you can get data in like corrupt state. So you kind of need to like keep a copy of that and then save that off while it's being changed. I know like backups also like deal with dirty flags to figure out like what to back up, what to save to state. And you could do incremental saves too, I suppose. I don't think your dirty param conversion there is equivalent. If you pass false, you'll set the flag to false. I don't think the C++ code would. unless previous dirty value was also false. Okay, so my this.dirty is not correct. Like, it's not doing that. The only equivalent that I can think of would be dirty equals dirty or this dot dirty. Something like that. Yeah, that's the only, I think this is like the closest to it then that I can get to. Dirty equals dirty or dirty equals 1 or like true at that point. Let's see. So let me put this in for Ootsbees. So this would be dirty equals, and then in here we're gonna have dirty. It has to be like double pipes in JavaScript, I think. This dot dirty equals true, like that, I think. Am I correct in translating that correctly? Alright, continuing on. How fine-grained is your dirty tracking? Imagine our pirate game lets players build and customize their pirate ship. Ships are automatically saved online so the player can resume where they left off. We're using dirty flags to determine which decks of the ship have been fitted and need to be sent to the server. Each chunk of data we send to the server contains some modified ship data and a bit of metadata describing where on the ship this modification occurred. If it's more fine-grained, say you slap a dirty flag on each tiny plank of each deck, you only process data that actually changed. You'll send exactly the facets of the ship that were modified to the server. If it's more coarse-grained, alternatively, we could associate a dirty bit with each deck. Changing anything on it makes the entire deck dirty. I can make some terrible joke about it need to be swabbed here, but I'll refrain. Or did you? You end up processing unchanged data. Add a single barrel to a deck, and you have to send the whole thing to the server. Less memory is used for storing dirty flags. Add 10 barrels to a deck, and you only need a single bit to track them all. Less time is spent on fixed overhead. When processing some changed data, there's often a bit of fixed work that you have to do on top of handling the data itself. In the example here, that's the metadata required to identify where in the ship the changed data is. The bigger your processing chunks, the fewer of them there are, which means the less overhead you have. And then see also, this pattern is common outside of games and browser-side frameworks like Angular. They use dirty flags to track which data has been changed in a browser and needs to be pushed up to the server. Physics engines track which objects are in motion and which are resting. Since a resting body won't move until an impulse is applied to it, they won't need processing until they get touched. This is moving bit is a dirty flag to note which objects have had forces applied and need to have their physics resolved. Oh, interesting. Okay. I could also imagine that, like in physics, if you're doing things where like let's think of like a pool game, like a billiards game, where you have balls on the table, and you're firing like a cue ball at another ball. Everything is like standing still. The cue ball is now like we suddenly hit it, so it moves. It then hits another ball, so we have to now set that flag to, okay, we now need to resolve, set its, new velocity, like apply a force, and then resolve those movements. We then hit other balls to then set their dirty bits, and then we start them moving, and then eventually come to staying still, and so then they like get set to back to standing still again. That being said, I'm not I still don't fully understand what I'm doing in this transform. Pipe exists in JavaScript. However, the C++ is probably using an equivalence between 1 and true. So the bitwise OR works. So if you're only using true and false values, the pipe would be equivalent. Okay, and so because I'm using true and false, then okay. So single pipe does exist in JavaScript. Yeah, I've not really played with bitwise in JavaScript at all. So that would explain why I haven't really seen that. Okay, that's good. That's good to see. So this is equivalent when I'm using true and false. If I'm not using true and false, or 1 and 0, something that's truthy and falsy, then I'm gonna need single pipe, which would be exactly what you have here. So let me replace this with that. I guess it's, yeah. There. Now, of course, this code isn't really runnable because I don't have anything working with transform origin. So we can't actually like truly test this out, or can we? We might be able to here. So let's open this up. Let's actually not go in there. Let's use a reel. Let's create ourselves a new window here. Open up node. All right, so in here, let's do let dirty equals false. If the C++ code really needed bitwise stuff, yes, I expect it doesn't though. Okay, so let's try a couple of these different things. So we have dirty or true. So that's true because dirty is false. Now if I do dirty or true like that, that's 1. And I guess we could just do these with like false or false is 0, false or true is 1. Is there such a thing as like equals to this? So can I now do dirty equals oh wait, I can't do something like that. So dirty is now 1. So can I do dirty pipe equals false? Dirty is still 1. Okay. I believe if you use the bitwise, then JavaScript is converting the true false to an int before applying. That seems to be what it's doing because I'm seeing that it's like 1s that I'm getting out of here. And so dirty is now 1, even though it was true false. Now if I set dirty back to true again, can I do dirty pipe equals to false? Dirty is 1 again. Now let's set dirty to false. And we'll do this one again. Dirty is now 0. Okay, so set dirty to true. If if I do dirty pipe equals to false, dirty is 1, which is like the equivalent of true. And if I wanted to convert this into like a Boolean again, I can do the really dirty trick of, I think, plus plus. Oh, it doesn't like that at all. Right, okay, so I can't really do that at this point in time. I have to do it in 2 lines. Then say like, okay, dirty plus plus equals plus plus dirty. Oh wait, I forgot, that's a pre thing. What is it? What is the thing that converts to Boolean? Bang bang. I am thinking about that. Okay, I was wrong side of the keyboard. Let's reset this back. Equals true. So if I do, you're right. Okay, thank you for that. So if I do, they're gonna have to do dirty pipe equals to like false, and then dirty equals bang bang dirty, and then that sets it back to this, which like sucks for this. Now if I just stay with like 1 and 0, I don't think that's a problem then. We can stay with like the bitwise operator. But if we play with Peekaboo, hello, good morning. So I would need to like I haven't really played with bitwise stuff very much, so I guess I'm not necessarily seeing where how super helpful it is to me. Let's see this. So if dirty is true, it's 1. So it's true, it just reassigns it to itself, but it also converts it to an integer. If it's false, it takes whatever the right-hand side is. Well, that makes sense. I think you're fine with the pipe. As I said, I don't think C++ really requires the bitwise stuff. It's just a habit of C or C++ coders. Okay. Yeah, that makes sense. Peekaboo, are the sales high for the game I released? No, but that's also because I never released a game. So, at least I've never sold a game for money. So, no, absolutely not. So we totally could do dirty pipe equals to this dot dirty, like that. Like that's something we could do here. But it would now be converting it to 1 and 0, and we'd probably want this to then be 1, if that's case with that. So now something with this, the origin and the transform. Like what are we doing in origin here? Sales per game release are infinite. Absolutely, yes. I have, because I've never released a game to sell or made a game that's sellable. I don't apologize for that. You didn't crash me. I have protections. Um, I have infinite possibility here. That infinite runner that we made, I mean, who knows? I could be a billionaire. Like, we could put it on Steam. I'm sure it'll, like, the Call of Duty. Why would anybody want to play that after they see my infinite runner? As I'm let's see. Okay, so it also has a method to get an origin transform, basically an identity matrix that means no translation, rotation, or scaling at all. So the origin does the calculation to like do all those rotations and everything else at that time. So is that something like it's like location? Like what are we doing here? So based upon this, are we, and because we're calling this statically here, because we're saying, okay, give us transform origin. Like we're calling origin off of transform like this. We're not passing it in anything. Yeah, I don't know. Not sure. So like, what this origin function is really doing. Like it says that it's getting an origin transform, basically an identity matrix that means no translation, rotation, or scaling at all. Is that the equivalent to like a location? I guess like it would be a vector, right? So like a I guess I can't really do it multi-line like that. A like x is 0, y is 0, rotation is 0. Something like that. Like it's just giving us a like an object like this. Now in combine, the only operation we need here is combine, so we can get an object's world transform by combining all of the local transforms along its parent chain. And so then we do other. And so we're getting like the original origin transform, which is absolutely nothing. It's like no, its x position is its y and its rotation. And then we're just sort of setting these in here as we go along. So when we call combine on this, so starting here, we create our root graph. We set that up. We haven't added anything into it. So we have this graph, new graph, we graph render with a transform origin on it. So that gives us this. So this render, we have a transform origin. and undefined coming in here. So this is essentially coming into this. So first run first pass parent world is that. And then also dirty is undefined. Then we move down to here. So dirty equals dirty or this dot dirty. So this is undefined. So it's definitely not going to be this. We're going to go to this dot dirty. So now dirty now is true. Okay, so if that dirty, so we are dirty at this point. So this dot world equals this dot local dot combine. So now we run this combine here, and we pass in the parent world, which is this thing. So this dot local dot combine. I don't know how combine. Like, I'd almost think we have to pass in two things, right? To have combine things together. World is also null. So even if I just return other straight back, did I just not? Let's see, combine takes a transform, which is an other. And when I call transform, or when I call combine, I just pass in the parent world, and it equals to that. But what combine does, I don't know. The only operation we need here is combine, so we can get an object's world transform by combining all the local transforms along its parent's chain. Am I supposed to be creating like a new transforms and like storing that? In the world? This is where it breaks down for me. I don't know what combine is doing. So like in a first pass, other is that. I don't necessarily have anything to, let's see, okay. So if I return an object like this, and we just say x is 0, y is 0, rotation is 0. So let's actually do that. I'm getting other, which is this thing, but I don't know what to combine it with. So we have this public static transform. Okay, so we need to create a new transform at some point in time. But we don't know what transform is going to hold. Is there ever a new transform? No, there's no new transform in this page. Now I have this local combine. Okay, so if we're calling local combine, and combine is only on transform, and there's no combine on like one of these, so local equals transform origin. Does this give us a new transform? Is that what this is? So should I be doing a constructor here? And what's really happening here is we're saying this dot x equals 0. This dot y equals 0. This dot rotation equals 0. When we do an origin, we're returning new transform like that. Okay, now in other, we get an other transform. So I actually want to rename this other transform so we know exactly what that is. Other is this thing right away. And now we want to combine these together somehow. And it was suggesting that it's like maybe multiplication is what we're doing. So matrix multiplication, where we have to we then say this dot x times equals other transforms dot x, this dot y times equals other transforms dot y, this dot rotation like that. Okay, that makes a lot more sense. So then transform origin, we call this, we get a new transform that comes into graph render. In render, we have our parent world. We then call combine on that because we have now an actual transform instance. We pass it the parent world, which is that just basic transform that we have. So it combines them together. So 0 times 0 is 0, nothing happens. We set dirty to false because we've combined the world. We've done the transform. Then we render the world and pass it the mesh of the world. Then we have to loop through everything and have it render, which does the combine for it too. Okay, I think that's what I was missing. It makes a little bit more sense, but I think I would need to like play with it to actually see it working, to see it like actually do something and see like the transforms happening and then like things moving across the screen. So I don't, yeah, that's something I'm gonna add to my like personal list to sort of like return back to. But this is like an interesting idea for it. I'm gonna go ahead and send this on up to GitHub. Dirty flag here. Okay, so read through dirty flag feature or chapter. Implemented or transformed, implemented, translated, converted, converted examples to JavaScript. You always like the Git Kraken octopus animation. I know it is really nice. Gonna push this on up. I have the code available to us. It is in the bang repo command. So if you want to go take a look at that code, it is in there. It's in the playgrounds dirty flag sort of folders inside of there. And so with that, I think we're about done. So I'm gonna put in the marker to finish this off. I will also have a link to this code